Okay, so next up is Xiangyu Jin, and she'll be telling us about new model independent constraints on the NGM neutral fraction.
Hello everyone, I'm Xiangyu. I'm a first-year grad student at University of Arizona, and thanks for this amazing chance to present our work at SAZERAC conference. Today, I'm going to talk about our recent work that uses high-range quasar to derive model-independent constraint on the IgM neutral hydrogen fraction up to range 6.8. My collaborators on this project are Professor Xiangyu Jin, Dr. Yang, and Dr. Fei Wang. Before I talk about our measurement, I want to give a very brief view about reionization. Reionization is an important landmark in the evolution of intergalactic medium. So it's very crucial to investigate how the neutral hydrogen fraction is evolving during this epoch of reionization. The neutral hydrogen fraction can be measured from high-redshift galaxy or high-redshift quasar. But through this high neutral hydrogen fraction measurement from high-redshift quasar, which is shown by the figure here, you can find there is a very clear gap in the measurement at around redshift 6.5. Thus, therefore, in our study, we want to use high-redshift quasar to constrain the neutral hydrogen fraction in this redshift range. There are several commonly used methods to probe this neutral hydrogen fraction with high-redshift quasars. For example, we can study the transmission spike in Lyman alpha and Lyman beta forest to measure neutral hydrogen fraction. The neutral hydrogen fraction can also be measured from the mean free path of ionizing photons. From individual quasars, the neutral hydrogen fraction can be measured from the damping ring feature in the spectrum. The size of quasar proximity zones can be also used to measure the neutral hydrogen fraction. But all of those four methods I just mentioned, they are more or less model dependent, whether on the IgM model or quasar intrinsic spectra or quasar lifetime. The only model-independent constraint from high-range quasar is studying the dark pixels in Lyman alpha and Lyman beta forest. This is the method we are using in our study. This method about use dark pixel in Lyman alpha and Lyman beta forest was first used by Magellan 2011. The basic idea is that they beam the spectra in Lyman alpha and Lyman beta forest on a larger pixel scale to get a higher emitting optical depth. So those beam spectra are shown by those vertical bars here in this figure. For the highly ionized region, they will appear as very bright pixels in this figure. But for the region that are not very highly ionized, they can attenuate the flux emitted by the quasar to a very low level. Thus, they will appear as dark pixels in this figure. We can adopt criterion to identify those dark pixels. For example, here, Magellan used a 2 sigma noise level, which is shown by this red solid line, to identify dark pixel. If a pixel has a flux smaller than 2 sigma noise, it will be identified as a dark pixel and plotted in black in this figure. The current fraction of this dark pixel will be corresponding upper limit on neutral hydrogen fraction. And this constraint doesn't depend on any model assumption, such as the model of reionization model or quasar intrinsic spectral shape. Thus, we are using this in our study. So we set 53 high-redshift quasar. Their redshift range is about 5.73 to redshift 7.085. Here is a redshift distribution of those quasars. We have spectra from BLT, Keck, MMT, Magellan, LBT, and Gemini. For the wavelength range of Lyman alpha forest, we are using this wavelength range in the red frame in our study. The shorter wavelength cut is to exclude oxygen 6 emission in the quasar intrinsic spectrum, and the longer wavelength cut is to avoid contamination from quasar proximity zone. For the Lyman beta forest, we are using this wavelength range in our study. The shorter wavelength cut is to exclude Lyman gamma emission and Lyman gamma forest. The longer wavelength cut is to match to the same absorber redshift as the longer wavelength cut of Lyman alpha forest. Then we follow the method in Magellan 2011 to beam the spectrum and use this 2 sigma noise level to identify the dark pixels in our spectrum. We calculate the fraction of dark pixels from individual quasars and derive their average value in each redshift band. And we use Gemini statistic to calculate their 1 sigma scatter. Here, when we calculate the dark pixel fraction, we exclude pixel with a limiting optical depth smaller than 2.5 The limiting optical depth in our study is only used to indicate the quality of pixel to probe the neutral hydrogen. If a pixel has a higher limiting optical depth, this means it has a higher ability to probe the neutral hydrogen. And here is our measurement. The constraint from Lyman alpha force are shown by those blue upper limits, and constraint from Lyman beta force are shown by those red upper limits. Apart from these two constraints, we also get a combining constraint from Lyman alpha and Lyman beta force, and those are shown by those magenta upper limits. In this constraint, a pixel is dark only if it's below 2 sigma noise, both in Lyman alpha and Lyman beta force. And this combining constraint from Lyman alpha and Lyman beta force give us the tightest constraint on the neutral hydrogen fraction. From this combining constraint, it puts an upper limit on neutral hydrogen fraction about 35% at redshift 5.5. And this upper limits increase to about 80% at redshift 6.3, also at redshift 6.5. Later, this upper limit on neutral hydrogen fraction increased to about 95% at redshift 6.7. And those measurements are the first constraint from dark pixel study in those redshift range. Later, we use a higher limiting optical depth cut to select pixel with very high ability to probe the neutral hydrogen. And the result plotted with pixel with high limiting optical depth cut at 4.5 is shown on right-hand side. And as a comparison here, I also present this plot I showed on the last slide. This is plot with a smaller limiting optical depth cut on pixel with at 2.5. And on each figure, the number of pixels used to calculate this dark pixel fraction is shown on the upper panel. With this high limiting optical depth cut at 4.5, we can find it dramatically reduced the number of pixels used to calculate dark pixel fraction. Because at high redshift end, because the sky is very noisy at high redshift end, so we don't have many pixels with high limiting optical depth to calculate the dark pixel fraction. Thus, with a high limiting optical depth cut at 4.5, we can no longer put a valid constraint on the neutral hydrogen fraction, except for one. But with this high limiting optical depth cut, it can make the constraint at lower redshift end tighter. So compare with the upper limits here, you can find the upper limits with a higher limiting optical depth cut looks lower. Furthermore, we present more constraint on the neutral hydrogen fraction from other high redshift quasar study. The measurements on neutral hydrogen fraction from effective optical depth in Lyman alpha forest are shown by these black squares and green squares. They put a lower limit about on neutral hydrogen fraction about 10 to -4 at redshift 6. At higher redshift range, there are some individual measurements on neutral hydrogen fraction from the quasar damping wings. They are shown by those hexagons here. And from those measurements from quasar damping wings, you can find they are pretty diverse in the measured neutral hydrogen fraction. The reionization history derived from Planck is shown here. The 1 sigma confidence interval is shown by this dark gray shaded region. And the 2 sigma confidence interval is shown by this light gray shaded region. We present our upper limit on neutral hydrogen fraction at lower redshift end by those magenta upper limits, because here we want to get a tighter constraint on the neutral hydrogen fraction with a higher limiting of the depth cut at 4.5 to get a tighter upper limits. And as a comparison here, we also include the result from Magellan 2015 by those blue upper limits. They also use dark pixel to put upper limit on neutral hydrogen fraction in this redshift range. And our results are consistent with their measurements. At higher redshift range, because the sky is very noisy, so here we use a smaller limiting optical depth cut at 2.5 to derive this upper limit on neutral hydrogen fraction. And our results are constrained about 80% on the neutral hydrogen fraction at redshift 6.3 at 6.5. And this upper limit on neutral hydrogen fraction increased to about 95% at redshift 6.7. And overall, our upper limit on neutral hydrogen fraction increased very fast with redshift. And this might indicate that the evolution of IgM neutral hydrogen fraction is evolving very fast in this redshift range. Now let me briefly summarize our work. So we derive new model-independent upper limits on the IgM neutral hydrogen fraction from 53 high-redshift quasar based on the dark pixels in the lambda alpha and beta first. And our result comes to the upper limit on neutral hydrogen fraction of 80% at redshift 6.3 and also 80% at redshift 6.5. This upper limit on neutral hydrogen fraction increased to about 95% at redshift 6.7. This very fast increase in the dark pixel fraction might imply a fast evolution in IgM neutral hydrogen fraction in this redshift range. Let me end it here, and thank you very much for listening. I'm happy to take any questions.
Thank you very much for a nice talk. We'll wait 20 seconds or so, and then Steve will ask the first question.
All right, very nice talk, Xiangyu. The first question is, how can you constrain the mean neutral hydrogen fraction from the dark pixel fraction? Doesn't it require you to assume the density PDF?
So let me go back to that slides. So the basic idea is that for the highly ionized region, there are bright pixels. So you just take the opposite of this highly ionized region and use the dark pixel to put upper limit on neutral hydrogen fraction. And I have a backup slide for this. So for this dark pixel, so it's intrinsic is resolved by neutral hydrogen fraction. Neutral hydrogen is just intrinsically have zero flux, right? So, but there might be some two scenario corresponding to this dark pixels in the observed spectra, but they're associated with quite different neutral hydrogen fraction. So for when we observe a dark pixel, we don't know whether that's 100% neutral or something else. So we can only use this to put up limit on hydrogen. I hope this answers your question.
Okay. So next question is, in Magrier 2015, they used negative pixels to estimate the dark fraction. Have you checked whether that makes a difference to your limits?
So we tried this a little bit, but because our study has some when we use this 2 sigma noise level, the dark pixel fraction is already pretty close to 1. So it means that when we use the definition of dark pixel, when we count the number of pixels with negative fluxes, we might have just more than 50% pixels with negative fluxes. So if we double that fraction, you will give a fraction more than 1. So I don't think it's very physical for that. And also because for the sky is very noisy at high redshift end, so sometimes the background subtraction is just a little bit over subtracted. So we have some slightly negative offsets in the flux. So that will cause some problems when we use that definition for the high redshift.
There are a couple questions about the bin size or the pixel size. Could you define what you mean by pixel, and how do you motivate that definition, and how do the results change depending on the pixel size?
Okay, so in our study, we only set this pixel size. So this is about 3.3 microparsec in co-moving distance. So because this, we use this pixel size for all the sight lines, and we don't quite test how this pixel size will change our result. I guess probably that's the next step. And the reason why we want to choose a larger pixel size because the limiting object depth is higher for a larger pixel size.
Okay, thank you very much for a nice talk again. You have a couple other questions, so please respond at your convenience in Slack.